The object appears first as a smudge on digital sensors, a faint trace of reflected sunlight captured by telescopes scanning the outer reaches of the solar system. It moves through the darkness with a velocity that immediately marks it as unusual, too fast for a typical comet, following a trajectory that originates from somewhere beyond the Sun's gravitational dominion. The astronomers who first notice it run the calculations 3 times, then 4, checking for instrumental error or orbital decay in their equipment. The numbers remain consistent. This visitor does not belong to the family of objects born alongside Earth and its planetary siblings. It comes from interstellar space, from the vast emptiness between stars, carrying momentum imparted by encounters and ejections that occurred before humans walked upright, perhaps before humans existed at all. They assign it a designation 3I Atlas. The I denotes interstellar origin. The third such object confirmed entering the solar system after Oumuamua in 2017 and Borisov in 2019. The discovery itself represents a triumph of modern observation. Only in recent decades have telescopes achieved the sensitivity to detect these wanderers. For all of human history prior to this technological moment, interstellar objects passed through unnoticed, invisible ghosts threading between the planets. How many came before, unobserved? Their stories lost to the silence of deep time. The universe offers no archive of missed encounters. The object measures perhaps several hundred meters across, though its exact dimensions remain uncertain at this distance. Its surface likely consists of ice's water, carbon dioxide, methane, ammonia mixed with silicate dust and organic compounds, the frozen remnants of whatever stellar nebula birthed it. These ices have remained undisturbed by solar radiation for millions or billions of years, preserved at temperatures barely above absolute zero. Now, as 3 Atlas approaches the inner solar system, the sun's warmth begins to wake these ancient frosts. A faint coma develops, a halo of sublimating gas that makes the object slightly easier to track but complicates mass estimates. Is it mostly ice, prone to fragmentation, or does a denser core hide beneath the volatile exterior? The trajectory becomes the focus of intense scrutiny. Every observatory with the capability trains its instruments on this moving speck, gathering photons to refine the orbital elements. Each new measurement narrows the uncertainty, collapsing the probability cloud that describes where 3I Atlas might go. Most paths lead to harmless outcomes, a swift passage through the solar system, perhaps a close approach to Jupiter or Saturn that provides spectacular imagery and valuable scientific data, then a departure back into interstellar space, trajectory altered by the sun's gravity. The object would leave as it arrived, a temporary guest in a system not its own. But within the mathematics, within the margins of error that still persist despite dozens of observations, a narrow corridor exists, a specific set of gravitational interactions, a precise angle of approach, a particular timing relative to Jupiter's orbital position. These factors align to create a possibility so remote it borders on abstraction, yet remains non-zero. The object could be deflected, its path could curve inward rather than outward, and in that curving, in that gravitational reshaping of momentum, Earth might lie waiting. The probability remains vanishingly small. Astronomers speak in percentages with many zeros after the decimal point. 1 in several million, perhaps. 1 in tens of millions. The uncertainty itself contains uncertainty, too few data points to collapse the wave function of possibility into certainty. Yet the human mind, evolved to detect threats in rustling grass and shadows at cave mouths, seizes upon this remote chance and amplifies it. News outlets begin their coverage. Social media fills with speculation, with artists' renderings of impact, with breathless comparisons to the dinosaur-killing asteroid that struck 66 million years ago. The scientists continue their observations, patient and methodical. They know that probability favours the mundane, that the universe tends toward near misses rather than collisions in the vast emptiness of space. The solar system consists primarily of nothing planets, and asteroids represent tiny islands in an ocean of vacuum. To strike Earth requires threading a needle across interstellar distances, hitting a target 8,000 miles wide after travelling trillions of miles through the dark. The cosmic improbability of such precision remains staggering, yet Earth's surface bears the scars of past impacts. Meteor crater in Arizona, the buried Chicxulub structure beneath Mexico's Yucatan Peninsula, the ancient Vredefort Dome in South Africa, eroded remnant of a collision that occurred 2 billion years ago. These wounds in stone testify to a simple truth: improbable events, given sufficient time, become inevitable. The question shifts from if to when, a matter of timescales rather than possibilities. For now, 3C Atlas continues its approach, indifferent to the attention trained upon it. Following the geodesics of space-time with mechanical precision, it carries no intent, no consciousness, no awareness of the planet-bound observers tracking its every movement. It simply falls, as all objects fall, along the curved geometry of gravity's invisible architecture. The worst-case scenario remains theoretical, a mathematical exercise in destruction. But mathematics describes the universe with unsettling accuracy, and somewhere in those equations, disaster sleeps, waiting for the right coefficients to wake it. Only took 4 billion years to develop the ability to see this coming. The universe moves slowly when it bothers to move at all. The question of origin haunts every observation. Where did 3 Atlas begin its journey? Which star once held it in orbit before gravitational perturbations cast it into the darkness between suns? The astronomers work backward through the object's trajectory, tracing its path through galactic space, accounting for the sun's motion around the Milky Way's centre, for the subtle gravitational tugs of nearby stellar systems, for the slow drift of stars over millions of years. The calculations require modelling the galaxy itself, treating hundreds of billions of stars as a gravitational field through which this single fragment moves. The most likely candidates emerge from statistical analysis rather than certainty. Perhaps 3 Atlas originates from a stellar system 30 light-years distant, ejected during the chaotic early phase when young planets and planetsimals engaged in violent orbital reshuffling. Or perhaps it comes from farther still, from a system long since dispersed or destroyed, its parent star now vanished into the galaxy's general population. The object itself carries no identifying markers, no isotopic signatures that could pinpoint its birthplace with precision. It remains anonymous, a citizen of interstellar space with papers that reveal only the broadest geographic origins. The mechanism of ejection follows well-understood principles. In any young stellar system, planetary formation involves countless collisions and gravitational encounters. Small bodies, comets, asteroids, planetesimals accumulate into larger worlds through accretion, but not all bodies merge. Some receive gravitational assists from forming gas giants, velocity boosts that accelerate them beyond the system's escape velocity. They become interstellar nomads, untethered from the star that witnessed their formation. Current models suggest every stellar system ejects billions of such objects during its first 100 million years. The galaxy fills slowly with these wanderers, a vast population of orphaned fragments drifting between the stars. 3I Atlas likely spent billions of years in transit, at interstellar velocities of tens of kilometers per second. Crossing even the relatively short distances between neighbouring stars requires millions of years. During this journey, the object experienced conditions fundamentally different from those within solar systems. The temperature of interstellar space hovers only a few degrees above absolute zero. Cosmic rays, high-energy particles from supernovae and other violent events bombarded the surface, gradually altering the chemical composition of surface ices, creating compounds that could never form in the warmer, denser environments near stars. The scientific value of such an object exceeds almost any other target in the solar system. 3I's Atlas carries material from another stellar environment, compounds that formed under different conditions from those that produced Earth's oceans and atmosphere. Spectroscopic analysis reveals absorption lines corresponding to familiar molecules water, methane, carbon monoxide, but subtle variations hint at different formation histories. The ratios of deuterium to hydrogen, of carbon-13 to carbon-12 of various nitrogen isotopes, these provide clues to the temperature and pressure conditions in the nebula, where this object first condensed from gas and dust. Missions to intercept and sample interstellar objects have been proposed but never funded. The technical challenges remain immense. By the time an object is detected and its trajectory calculated, it has already passed closest approach to the Sun and begun accelerating outward. Reaching it would require spacecraft capable of extraordinary velocity changes, far beyond current propulsion technology. The objects move too fast, appear too briefly, and travel too far for human engineering to pursue them effectively. Humanity watches them pass, gathering data from photons, but unable to touch. Some researchers propose that interstellar objects might carry not just chemistry, but biology. Panspermia, the hypothesis that life could spread between stellar systems via natural transport mechanisms, finds renewed interest with each interstellar visitor. Could microorganisms survive the journey? Frozen in ice for millions of years? Protected from radiation by meters of overlying material, laboratory experiments suggest certain extremophils could endure such conditions, entering dormant states that persist indefinitely at cryogenic temperatures. If life arises readily wherever conditions permit, then interstellar space might function as a slow dispersal mechanism, seeding sterile worlds with biological potential. The hypothesis remains unproven and perhaps unprovable without direct sampling. Even if 3I Atlas carries dormant microbes within its icy matrix, detecting them from Earth-based observations would be impossible. The spectroscopic signatures of life-complex organic molecules, certain mineral patterns, atmospheric disequilibria require close proximity or atmospheric analysis. An object without atmosphere, tumbling through vacuum, reveals little of its internal composition to distant observers, yet the possibility lingers in scientific discourse, a tantalizing uncertainty. If 3 Atlas impacts Earth, would it deliver not only kinetic energy but genetic material? Would alien biochemistry, however primitive, contaminate the impact site and surrounding regions? The question mixes catastrophe with curiosity, extinction with possibility. Of course, at impact velocities measured in tens of kilometers per second, any biological material would face temperatures exceeding 10,000 degrees Celsius. Organic molecules would disintegrate, proteins denature, DNA shatter. The energy of collision sterilizes more thoroughly than any autoclave. The object continues inward, crossing the orbit of Neptune, then Uranus. Each planet it passes offers a gravitational influence, minute perturbations to its trajectory that accumulate into meaningful deflections. The solar system functions as a complex dynamical environment, where every mass affects every other mass, where predictions require accounting for countless interactions simultaneously. Chaos theory applies here. Small changes in initial conditions produce vastly different outcomes. A difference of meters in 3I Atlas's current position could translate to millions of kilometers in its final trajectory. The uncertainty cone narrows with each observation but never collapses to zero. Ground-based telescopes track it through the night. Space-based observatories, free from atmospheric distortion, capture sharper images. Amateur astronomers around the world contribute sightings, building a crowdsourced database of positional measurements. The object belongs to everyone and no one, a shared focus of attention that briefly unites the fragmented human community in common observation. How many such objects pass through undetected for each one spotted? The question remains unanswered. Detection depends on size, distance, reflectivity, and the direction of observation. Small objects or those approaching from angles poorly covered by major observatories slip through unnoticed. The census of interstellar visitors remains incomplete, a sampling bias masquerading as complete knowledge. 3 Atlas represents what can be seen, not what exists. The distinction matters more than comfort allows. The mathematics of orbital mechanics reduces catastrophe to equations. Every trajectory through space follows deterministic laws. The elegant geometry of gravitational fields and momentum vectors. Given perfect knowledge of an object's position, velocity, and the distribution of mass in the solar system, prediction becomes calculation. The future unfolds from the present with mathematical certainty, constrained only by the precision of measurement and the completeness of the model. But precision remains elusive. Each observation of 3i Atlas carries error bars, uncertainty ranges that reflect the limitations of instruments and atmospheric interference. Photons travel across millions of kilometers, their paths bent by gravitational lensing, scattered by interplanetary dust, refracted through Earth's turbulent atmosphere. The recorded position contains noise. The measured velocity includes accumulated errors from multiple observations. These uncertainties propagate through calculations, expanding as predictions extend further into the future. A position uncertain by 10 kilometers today becomes uncertain by 100,000 kilometers next month, by millions of kilometers next year. Orbital analysts construct probability maps, visualizations of where 3i Atlas might travel. These maps resemble clouds more than lines, diffuse regions of possibility density that spread wider with time. The highest probability regions trace the most likely paths, graceful curves that sweep past Earth at comfortable distances, trajectories that carry the object through the inner solar system and back out toward interstellar space. But the clouds contain tails, low probability extensions that reach toward Earth's orbital path. These tails represent the scenarios that keep risk assessment specialists awake during long nights, the outcomes that sit at the edge of statistical significance but refuse to vanish entirely. Jupiter dominates these calculations, the gas giant, with its mass 300 times Earth's and its influence extending across vast reaches of space, functions as the solar system's gravitational keystone. Objects passing near Jupiter experience trajectory changes measured in kilometers per second, enough to transform harmless passages into dangerous approaches. The timing of 3i Atlas's trajectory relative to Jupiter's position in its 12-year orbit becomes critical. If the object passes through a specific region of space when Jupiter occupies a particular position, the gravitational deflection could redirect it inward. If the timing differs by mere days, the deflection sends it outward instead, accelerating its departure from the solar system. This sensitivity to timing reflects the three-body problem, one of classical physics' most famous unsolvable equations. Two bodies, say, the Sun and 3 Atlas, follow perfectly predictable orbits, their motion describable through closed-form equations. Add a third body, Jupiter, and analytical solutions vanish. The system becomes calculable only through numerical integration, step-by-step simulation that approximates the continuous dance of gravitational interaction. Small errors in any step propagate into larger errors downstream. Chaos emerges not from randomness but from deterministic sensitivity to initial conditions. The narrow corridor of danger exists within this chaotic regime. If 3 Atlas passes Jupiter at a specific distance, at a specific angle, with a specific velocity, the resulting deflection curves its path inward. The deflection must be precise too much, and the object plunges into the Sun or achieves enough velocity to escape the solar system entirely. Too little, and it continues past Earth without incident. The window measures perhaps a few thousand kilometers wide at Jupiter's distance, a tiny target in a region of space millions of kilometers across. Earth itself moves through this geometry, following its elliptical path around the Sun at 30 kilometers per second. The planet sweeps through space like a broom, clearing a cylindrical volume roughly 25,000 kilometers in diameter, Earth's physical width, plus the gravitational focusing effect that draws nearby objects inward. For 3 Atlas to strike Earth, It must arrive at a specific point in space at the exact moment Earth occupies that same point. The coordination required staggers comprehension. 2 objects, each following independent paths determined by ancient momentum and gravitational fields, must converge in location and time with precision measured in seconds and kilometers. The probability of such convergence depends on factors beyond current observational capacity. Does 3I Atlas outgas asymmetrically as it approaches the Sun, creating rocket-like thrust that alters its trajectory in unpredictable ways? Does its rotation change, affecting how sunlight pressure influences its path? Does it fragment, breaking into multiple pieces that follow diverging trajectories? Comets frequently display such behaviors, their activity driven by internal structure and composition that remain invisible until solar heating begins. 3I Atlas shows some signs of cometary activity, the developing coma, the slight brightening as volatile ices sublimate, but whether this activity changes its trajectory remains uncertain. Ground-based radar systems ping the object when it approaches within a few million kilometers of Earth, close enough for radio signals to make the round-trip journey and return detectable echoes. The radar data provides precise distance measurements, accurate to within meters, and reveals details about the object's rotation rate and surface properties. These measurements collapse some uncertainty, but introduce new questions. The radar signature suggests an irregular shape, possibly elongated or binary, 2 smaller objects orbiting each other, held together by mutual gravity. If the system is binary, its dynamics become even more complex. The internal orbital dance adding another variable to the trajectory calculation. Astronomers recalculate continuously as new data arrives. Each observation updates the probability distribution, shifting density away from some trajectories and toward others. The process resembles Bayesian inference, the gradual refinement of belief through accumulated evidence. Early probability maps showed vast uncertainty clouds encompassing multiple outcomes. Recent maps show tighter distributions, narrower possibility spaces. The most likely scenarios solidify. The worst-case scenarios remain possible but increasingly implausible. Yet implausible differs from impossible. The mathematical tail extends toward catastrophe, thin but non-zero. Risk assessment involves not just probability but consequence. A low probability, high consequence event can dominate rational decision-making despite its statistical improbability. A 1 in 10 million chance of global catastrophe still warrants attention, preparation, analysis. The expected value calculation probability multiplied by impact produces numbers that demand response. The corridor of danger narrows with each passing day, each new observation. But corridors, however narrow, remain corridors, and 3I Atlas continues to fall through them, following geodesics that care nothing for human concern. Only took 3 centuries of orbital mechanics to achieve this level of prediction. Still guessing, really, just guessing with better mathematics. The ice remembers. Within the frozen matrix of 3I Atlas, molecules preserve their arrangement from the epoch of formation, locked in place by temperatures that prevent thermal motion, that silence the random walk of atoms seeking lower energy states. Water ice dominates the composition, as it dominates most cometary bodies. But this ice differs from terrestrial varieties. The deuterium ratio, the abundance of heavy hydrogen with its extra neutron, suggests formation temperatures around 20 to 30 Kelvin, conditions found in the outer regions of protoplanetary disks, where gas giants accrete and icy bodies condense. Spectroscopic observations reveal absorption features corresponding to carbon monoxide, carbon dioxide, and methane. These volatiles remain mixed throughout the ice rather than separated into distinct layers, indicating rapid freezing from a well-mixed gas phase. The formation process likely occurred quickly by geological standards, perhaps over a few thousand years as the parent stellar nebula collapsed and cooled. The ices trapped other compounds as they formed ammonia, formaldehyde, hydrogen cyanide, simple molecules containing the elements necessary for more complex chemistry, but frozen before reactions could proceed. Organic compounds appear in the spectroscopic data as well, though their exact identities remain uncertain at this distance. Long-chain hydrocarbons, possibly. Aromatic molecules, perhaps. Amino acids, maybe. Though confirming their presence would require direct sampling and analysis. These organics form naturally in cold molecular clouds through surface chemistry on dust grains. UV radiation driving reactions that would never occur in warmer environments. The interstellar medium functions as a vast chemistry laboratory, synthesizing complexity from simplicity across light years of space and millions of years of time. Cosmic ray bombardment has altered the surface composition during 3I Atlas's journey through interstellar space. High-energy particles from distant supernovae and stellar winds penetrate meters into the ice, breaking chemical bonds, creating radicals, driving reactions through radiation chemistry rather than thermal energy. The surface layers likely contain compounds unknown in the inner solar system, exotic ices and tars created by processes that operate only in deep space. These materials remain stable only at cryogenic temperatures. As through Atlas approaches the Sun, warming begins to dismantle these fragile structures, sublimating the most volatile components and leaving behind a lag deposit of less volatile material. The developing coma consists primarily of water vapor and carbon monoxide, gases streaming away from the warming nucleus at several hundred meters per second. Sunlight ionizes some molecules, creating a faint ion tail that points directly away from the Sun, shaped by the solar wind's magnetic field. Dust particles liberated from the ice form a separate tail, curved by radiation pressure and following slightly different trajectories than the gas. This dust consists of silicate grains and refractory organics, the non-volatile residue that accumulated in the original protoplanetary disk and became incorporated into the comet during formation. The dust grains themselves carry stories, each particle formed in a specific environment, some condensed from cooling gas around an earlier generation of stars, others arrive from interstellar space already solid, survivors of previous stellar systems destroyed by supernovae or planetary nebulae. The grains show varying compositions, reflecting diverse origins. Some contain crystalline silicates, minerals that require high temperatures to form and must have originated near a star. Others show amorphous structures, materials that never experience significant heating. This mixture indicates that the protoplanetary disk that birthed 3I Atlas combined local and imported materials, blending the stellar system's native products with ingredients from the broader galaxy. Pre-solar grains, microscopic particles that predate the solar system, have been found in meteorites that reached Earth. Their isotopic compositions impossible to produce in the Sun's nebula. These grains originated in other stars, survived the interstellar journey, and were incorporated into new bodies when the solar system formed. 3I Atlas likely contains similar pre-solar materials, possibly from its parent stellar system, possibly from even earlier generations. The object functions as an archive, a collection of samples from multiple epochs and locations compressed into a single body. The scientific community dreams of analysing such material directly. Current missions carry only remote sensing instruments, unable to capture physical samples. The James Webb Space Telescope observes 3I Atlas in infrared wavelengths, detecting thermal emission that reveals surface temperature and composition. Ground-based spectrographs dissect the light reflected and emitted by the coma, identifying molecular species through their unique absorption and emission patterns. But spectroscopy provides only bulk composition, averaged across large areas. The detailed mineralogy, the grain-scale textures, the subtle isotopic variations, these remain inaccessible without physical samples analysed in terrestrial laboratories. If 3I Atlas were to impact Earth, it would deliver such samples in catastrophic abundance. The collision would vaporize most material, heating it to temperatures that erase chemical memory and homogenize isotopic distributions. but some fraction, perhaps a few percent, would survive as microscopic droplets and particles scattered across the impact site and ejected into the upper atmosphere. These fragments would cool quickly, quenching at temperatures low enough to preserve some chemical and isotopic signatures. Recovery teams could, in principle, collect these samples from the ejector blanket, sorting interstellar material from terrestrial impact melt. The irony of such scientific opportunity emerging from global catastrophe does not escape the researchers who study impact physics. Knowledge gained at such cost offers little comfort. Better to observe from safe distances, to gather photons rather than fragments, to let 3i Atlas pass unmolested through the solar system and continue its journey back into interstellar space. The ice remembers conditions from another stellar system, another epoch. It carries that memory inward toward the sun, sublimating slowly, releasing ancient volatiles into the contemporary solar wind. The molecules disperse, mixing with the sun's output, becoming indistinguishable from local material within days. The memory fades as the ice evaporates, information erased by entropy and thermal motion. What stories could those molecules tell? If molecules could speak, what conditions, what processes, what unimaginable contexts? The universe generates complexity and then destroys it, over and over, in endless cycles of formation and dissolution. Only took billions of years for that ice to travel here. Now it melts, pointlessly, contributing a few tons of water vapor to the solar system's vast inventory of volatiles. Everything travels so far to accomplish so little. The gravitational dance begins in earnest as 3i Atlas crosses the orbit of Saturn, entering the realm where planetary influences accumulate into measurable deflections. Saturn itself exerts minimal effect during this passage. The object's trajectory carries it far from the ringed giant, well outside the region where gravitational focusing becomes significant. But Saturn's presence alters the local geometry of space-time, creating subtle curvatures that bend 3i Atlas's path by fractions of a degree. These small deflections matter. In orbital mechanics, tiny angles at great distances translate to enormous positional differences closer in. Jupiter looms ahead, both literally and mathematically. The gas giant occupies a position in its orbit that places it disturbingly close to 3i Atlas's projected path. Not close enough for direct collision, the probability of impacting Jupiter hovers near zero, but close enough that gravitational interaction becomes inevitable. The encounter will occur in approximately 4 months, at a distance of roughly 3 million kilometers, about 8 times the distance between Earth and its moon. At such proximity, Jupiter's gravitational field dominates all other forces acting on the interstellar visitor. Orbital dynamicists model the encounter using N-body simulation software, programs that integrate the equations of motion for multiple gravitating bodies simultaneously. The simulations run thousands of times, each iteration testing slightly different initial conditions within the observational uncertainty range. The results populate a probability space, a multi-dimensional distribution showing where 3i Atlas might emerge from the Jupiter encounter. Most outcomes cluster around a single prediction. The object receives a gravitational boost that increases its velocity relative to the Sun, accelerating it outward on a hyperbolic trajectory that carries it back into interstellar space faster than it arrived. But some outcomes diverge. In roughly 3% of simulations, the Jupiter encounter deflects 3i Atlas inward rather than outward. The deflection depends on the precise geometry of closest approach to the distance, the angle, the relative velocity vector. These parameters remain uncertain within current observational limits. The object could pass Jupiter's orbit above the ecliptic plane or below it, sunward or spaceward, with velocity components that vary by several kilometers per second. Each variation produces different outcomes. The inward deflections carry 3i Atlas toward the inner solar system, toward the terrestrial planets. Mars becomes a possibility in some trajectories, though its small size and location make collision unlikely. Earth becomes possible in others, a subset of the inward deflection scenarios that number perhaps 1 in 3. Venus appears in rare cases, Mercury even more rarely. The probability tree branches at Jupiter, then branches again as the deflected object approaches the inner system, each branch representing a possible future that exists mathematically but not yet physically. The wild card involves non-gravitational forces. As 3I Atlas approaches the Sun, heating increases or more ice sublimates. The outgassing becomes stronger, creating thrust through the rocket effect. Gas molecules escaping from the surface carry momentum, and conservation of momentum requires that the nucleus recoil in the opposite direction. This thrust is small, measured in fractions of a millimeter per second per day, but it accumulates over weeks and months. The accumulated velocity change can reach meters per second, enough to shift the trajectory by thousands of kilometers. The direction of outgassing depends on the object's rotation and the distribution of volatile ices across its surface. If 3I Atlas rotates slowly, one hemisphere faces the Sun for extended periods, heating preferentially and outgassing asymmetrically. If it rotates rapidly, the heating averages around the surface and outgassing becomes more symmetric. Observations suggest a rotation period of roughly 18 hours, intermediate between slow and fast, with an axis orientation that remains poorly constrained. The outgassing direction therefore remains unpredictable, introducing stochastic behavior into an otherwise deterministic system. Some comets fragment under thermal stress. The temperature gradient between sun-facing and space-facing hemispheres creates mechanical stress in the ice. Volatile deposits beneath the surface heat and pressurize, potentially exploding and splitting the nucleus into multiple pieces. Comet Shoemaker-Levy 9 famously fragmented during a close approach to Jupiter in 1992, breaking into more than 20 pieces that subsequently impacted the planet in 1994, each impact releasing energy equivalent to millions of megatons of TNT. Could 3 Atlas fragment similarly? The question lacks a definitive answer. Fragmentation depends on internal structure, the porosity of the ice, the presence of structural weaknesses, the distribution of volatile and refractory materials. These properties remain invisible to external observation. Some comets prove robust, surviving multiple passages close to the Sun without breaking apart. Others disintegrate catastrophically, their nuclei crumbling into dust and dissipating over weeks or months. 3I Atlas could belong to either category, or exist somewhere between, partially fragmenting into a few large pieces rather than completely disintegrating. Fragmentation would complicate risk assessment dramatically. Multiple objects, each following slightly different trajectories, would require independent tracking and probability calculations. The collision cross-section would effectively increase instead of one object threatening Earth. Several would, each with its own impact probability. However, fragmentation also reduces individual masses. A single 1,000-meter object delivers far more kinetic energy than 1,000-meter fragments, even if the total mass remains constant. Smaller objects experience greater atmospheric deceleration, dissipating more energy before reaching the surface. The worst-case scenario arguably involves a single, intact nucleus rather than multiple fragments. The Jupiter encounter approaches. Telescopes track 3I Atlas nightly now, the object bright enough to detect with moderate instruments. Amateur astronomers photograph it, time-lapse sequences showing its motion against background stars. The coma extends several thousand kilometers from the nucleus, a diffuse envelope of gas and dust glowing faintly in reflected sunlight. The tail remains short, barely visible, underdeveloped compared to spectacular comets of the past. This object conserves its volatiles, sublimating reluctantly, holding its frozen memories close. Gravity cares nothing for human observation or concern. Jupiter simply exists, warping space-time according to its mass, creating geodesics that nearby objects follow. 3I Atlas will follow those geodesics, its path bending through the curved geometry, emerging with a trajectory determined by physics and chance. The dice tumble through vacuum, each face showing a different future. Most futures contain no catastrophe. Some do. The dice have not yet landed. Only took 4 billion years for Jupiter to become relevant to human survival. The planet simply orbits, indifferent, occasionally redirecting cosmic debris toward or away from the inner system. Sometimes a shield, sometimes a slingshot, no preference either way. Velocity distinguishes interstellar objects from their solar system cousins in ways that transcend mere numbers. A typical asteroid or comet native to the Sun's gravitational domain approaches Earth at speeds ranging from 15 to 30 kilometers per second. Velocities determined by orbital mechanics within the solar system's energy budget. These speeds, while substantial, remain bounded by the Sun's escape velocity at Earth's distance, approximately 42 kilometers per second. Objects born here cannot exceed this limit without external energy input. 3i Atlas carries velocity from elsewhere. Its motion through the galaxy relative to the Sun adds a component that solar system objects lack. Current measurements suggest an approach velocity relative to the Sun of roughly 55 kilometers per second. When gravitational acceleration is factored in, as the object falls deeper into the Sun's potential well, this velocity increases. At Earth's orbital distance, assuming an inward deflected trajectory, 3i Atlas would arrive at speeds approaching 70 to 80 kilometers per second, nearly double the velocity of typical asteroidal impactors. Kinetic energy scales with the square of velocity. Doubling the speed quadruples the energy. The impact energy delivered by 3 Atlas, if it were to strike Earth, would exceed that of a similar-sized solar system object by a factor of 4 to 9, depending on the precise trajectory and angle of approach. This energy manifests as heat, shock waves, and material deformation, all compressed into the first few seconds of collision. The physics of hypervelocity impact operates in regimes where materials behave more like fluids than solids, where shock waves propagate faster than sound, where temperatures reach those found in stellar interiors. The impact sequence begins with first contact, the moment when the leading edge of 3i Atlas touches Earth's atmosphere. At 70 kilometers per second, the object compresses atmospheric gases ahead of it faster than those gases can flow aside. The compression heats the air to plasma temperatures tens of thousands of degrees Kelvin, creating a brilliant fireball that outshines the Sun for observers unfortunate enough to be looking in that direction. This fireball represents energy transferred from the object's kinetic motion into thermal radiation, the first installment of energy release in a cascade that will continue for minutes. Atmospheric deceleration affects small impactors significantly, but large ones barely at all. An object hundreds of meters across, with mass measured in millions of tons, possesses too much momentum for the atmosphere to halt. Air resistance removes perhaps 1 or 2 kilometers per second of velocity, a rounding error in the overall energy budget. The atmosphere functions less as a shield and more as a witness, a thin envelope of gas that briefly records the passage of something cosmic before being vaporized in its wake. The object penetrates to the surface in less than 2 seconds after first contact. During this transit through the atmosphere, air ahead of the object reaches pressures exceeding 10,000 atmospheres, temperatures exceeding 50,000 degrees. This superheated, hyperpressurized air expands explosively, creating an atmospheric blast wave that propagates outward at supersonic speeds. The blast wave carries energy equivalent to hundreds of megatons of TNT, enough to flatten forests and structures for hundreds of kilometers in all directions. But this atmospheric energy release pales compared to what follows when 3i Atlas strikes solid ground. Impact occurs too quickly for human perception to register as a sequence of events. The leading surface of the object contacts the ground. Shock waves propagate into both the impactor and the target, traveling at several kilometers per second. These shock waves compress material to several times normal density, heating it to temperatures exceeding 10,000 degrees. The rear of the impactor continues moving downward at 70 kilometers per second, compressing the shocked material ahead of it. The ground beneath the impact point behaves like a liquid, flowing radially outward under pressures measured in megabars, millions of times atmospheric pressure. The energy density in the impact zone briefly exceeds that of nuclear detonations. Material vaporizes, dissociates into constituent atoms, ionizes into plasma. Rock that stood for millions of years as solid mineral assemblages becomes gas in microseconds. The vaporization creates a pressure cavity, a region where material has been converted from solid to gas with volumetric expansion ratios of thousands to 1. This cavity cannot be contained by the surrounding rock. It explodes outward and upward, beginning the excavation process that will form the impact crater. The excavation phase lasts minutes. Shock waves reflect off the free surface, converting compressive stress into tensile stress that fractures and ejects material. Rock and soil accelerate upward and outward, forming a curtain of ejecta that rises into the atmosphere. The fastest ejecta, accelerated to several kilometers per second, achieves escape velocity and leaves Earth entirely, becoming temporary satellites or escaping into interplanetary space. Slower ejecta follows ballistic trajectories, falling back to Earth hundreds or thousands of kilometers from the impact site. The ejecta blanket will eventually cover millions of square kilometers, burying the pre-impact surface under meters to tens of meters of broken, melted, and shocked material. The crater grows rapidly during the first minute. Material flows outward, excavating a transient cavity that reaches depths of several kilometers and diameters of tens of kilometers. The exact dimensions depend on impact velocity, angle, and the properties of target rock, its strength, porosity, and water content. Sedimentary rock excavates more easily than crystalline basement. Impacts into ocean create different crater morphologies than impacts into continental crust, the water moderating some effects while amplifying others. Gravity begins to modify the crater even as excavation continues. The transient cavity exceeds the strength of rock to support steep walls at such scales. The walls collapse inward, slumping into the crater bowl. The center rebounds upward, driven by elastic forces in compressed rock beneath the crater floor. For large impacts, this central uplift rises kilometers above its original position, sometimes reaching higher than the crater rim before collapsing back down. The final crater morphology includes a central peak or peak ring, terraced walls, and a diameter roughly twice that of the transient cavity. Seismic waves propagate through the entire planet. The impact generates earthquakes equivalent to magnitude 9 or greater, though the concept of moment magnitude becomes strained when applied to impact events. The seismic energy travels through the crust and mantle, diffracting around the core, focusing on the antipodal point, the location on Earth's surface directly opposite the impact site. Some models suggest antipodal focusing could trigger volcanic eruptions or intensify existing volcanism, though the evidence for this mechanism from past impacts remains ambiguous. The energy delivered to Earth in seconds exceeds the total annual energy release of all terrestrial earthquakes and volcanoes combined. The planet rings like a struck bell, vibrations detectable on seismometers worldwide for days afterward. The impact marks a moment in geological time, a sharp boundary in the rock record where everything changes, where the slow processes of erosion and deposition pause briefly to accommodate catastrophe. Only took 70 kilometers per second to deliver more energy than human civilization has generated in its entire existence. Speed matters, turns out, more than almost anything else in impact physics. The universe moves slowly, until suddenly it doesn't. The atmosphere offers its final defense, inadequate but not entirely without effect. As Thruai Atlas descends through progressively denser layers of air, the physics of atmospheric interaction becomes relevant for seconds only. But those seconds determine whether any warning reaches populations beneath the impact trajectory. Optical detection occurs first. The brilliant fireball created by atmospheric compression becomes visible from hundreds of kilometers away, brighter than the sun. casting sharp shadows in midday or turning night to false dawn. This light travels at 300,000 kilometers per second, arriving effectively instantaneously. Observers see the fireball before hearing any sound, before feeling any shockwave. The sonic boom follows, delayed by the finite speed of sound through air at 70 kilometers per second. 3i Atlas moves more than 200 times faster than sound. The object leaves behind a cylindrical shockwave, a supersonic wake that converges behind the trajectory and creates a boom corridor along the ground track. Windows shatter, structures shake. The sound resembles thunder but arrives from overhead in clear conditions, a roar without clouds, without lightning. The boom provides perhaps 10 to 20 seconds of warning, enough time to register confusion but not to reach shelter, not to escape the blast effects that will arrive moments later. Infrared satellites designed to detect missile launches register the atmospheric entry as a brilliant thermal signature, though the alert comes too late for meaningful response. The heat signature climbs into the petawatt range, briefly outshining entire regions of Earth's surface in infrared wavelengths. Automated systems flag the event, triggering alarms in monitoring stations, but the velocity and trajectory immediately identify this as non-military, as natural rather than adversarial. No nation launches anything at 70 kilometers per second. No human technology achieves such speeds from Earth's surface. The object strikes without further warning. There exists no time between atmospheric entry and surface impact for evacuation, for civil defense measures, for anything except realization. Modern impact monitoring systems, had they provided decades of advance notice, might have enabled deflection mission spacecraft dispatched to alter the object's trajectory through kinetic impact or gravitational tractor methods. But deflection requires years of preparation. Launch windows, trajectories carefully plotted to rendezvous with a threatening object at distances where small velocity changes translate to large positional shifts. 4 months from Jupiter, encounter to potential Earth impact provides insufficient time for any physical intervention. The atmosphere itself undergoes transformation during the brief transit. The cylindrical volume of air displaced by the object heats to plasma, expands explosively, creates a momentary vacuum cavity behind the object. This cavity collapses inward, generating secondary shock waves. The atmospheric disturbance creates optical effects, refraction patterns, pressure gradients visible as atmospheric waves, distortions in sunlight that propagate outward from the trajectory. High-altitude clouds within the blast radius dissipate instantly, vaporized by the thermal pulse. Lower clouds compress and darken before being shredded by shock waves. The impact location determines much about the subsequent catastrophe. An oceanic impact produces different immediate effects than a continental impact, though both lead to global consequences. Ocean covers 70% of Earth's surface, making it the statistically most likely target. Water provides minimal resistance to a hypervelocity impactor. It couples energy into the water column efficiently, creating shock waves that propagate through the ocean and generate tsunamis of unprecedented scale. A continental impact excavates solid rock, creating a crater that persists for geological timescales. The crater becomes a geographic feature, a basin that may fill with water or sediment, a scar visible from space for millions of years. The Chicxulub crater, buried beneath sediment in the Yucatan Peninsula, remains detectable through gravitational and magnetic anomalies 66 million years after formation. The Vredefort crater in South Africa, despite 2 billion years of erosion, still defines the local topography. 3i Atlas would create a similar permanent feature, a memorial in stone to the day the interstellar visitor arrived. The blast wave propagates outward from the impact site at hypersonic speeds initially, slowing to supersonic, then transonic, then subsonic as energy dissipates across expanding area. Peak overpressures near the impact site exceed 1,000 atmospheres, sufficient to pulverize rock and vaporize organic matter. At hundreds of kilometers distance, pressures drop to tens of atmospheres, still enough to collapse buildings and strip vegetation. At thousands of kilometers, the blast wave arrives as severe wind and pressure variations, breaking windows, damaging structures, but leaving some intact. The decay follows inverse square laws modified by atmospheric scattering and topographic effects. Thermal radiation from the fireball and the impact plasma travels outward at light speed, arriving before the blast wave. Within line of sight of the impact, everything combustible ignites. Wood bursts into flame, vegetation chars and burns, synthetic materials melt, human tissue, if exposed, suffers third-degree burns instantly. The thermal pulse lasts seconds, long enough to ignite but not to sustain combustion, creating millions of individual fires rather than a single conflagration. These fires spread or extinguish depending on local conditions, fuel load, moisture content, wind patterns. Beyond the horizon, geographic features provide some protection. Mountain ranges block thermal radiation and attenuate blast effects. Valleys channel shock waves, sometimes amplifying them, sometimes dispersing them. Underground structures offer the best protection, though even deep bunkers experience violent shaking as seismic waves arrive. Surface structures, no matter how well engineered, face forces beyond their design parameters within the severe damage radius. The severe damage radius extends hundreds of kilometers from the impact site for an object the size of 3E Atlas. Within this radius, survival depends on circumstance and chance being underground, being shielded by topography, being lucky. Outside this radius, but within thousands of kilometers, damage remains significant but survival becomes possible. Structures fail but collapse slowly enough that occupants might escape. Fires ignite but advance slowly enough that evacuation becomes feasible. The blast wave arrives with force but not instantly lethal force. Beyond several thousand kilometers, the immediate effects diminish to phenomena rather than threats. The ground shakes violently, but buildings designed for seismic activity might survive. The sky brightens unnaturally, then darkens as ejected material begins to fall. The distant rumble of impact, refracted through atmospheric layers, arrives as a sustained roar, audible across continents, a sound unlike any in human experience. Only took 2 seconds from atmosphere to ground, 2 seconds to transition from astronomical object to geological event. The universe measures time differently than humans do, but occasionally those timescales intersect, and those intersections tend toward violence. The crater forms according to physics that operates beyond human scales of intuition. In the first milliseconds, the impactor penetrates into the target rock, compressing and vaporizing material in its path. The kinetic energy converts to heat and pressure so rapidly that the distinction between projectile and target becomes meaningless. Both exist as plasma, a fourth state of matter where electrons separate from nuclei and everything flows, according to equations of state developed for nuclear weapons research and planetary science. The transient crater, the initial cavity excavated during the first minute, reaches depths of 15 to 20 kilometers and diameters of perhaps 50 kilometers. These dimensions depend on impact angle and velocity, on whether the object strikes vertically or obliquely, on the density and strength of target rock. Vertical impact excavate more efficiently, creating circular craters with symmetric ejector blankets. Oblique impact at angles less than 45 degrees from horizontal create elliptical craters and asymmetric ejecta, with the most material ejected downrange of the impact trajectory. The excavation flow involves material moving outward and upward simultaneously, following streamlines determined by the shockwave geometry. Rock that moments before formed stable geological formations now travels at hundreds of meters per second, behaving like a fluid with negligible viscosity. The material flows over and around itself, creating interference patterns and turbulence visible in the final ejecta distribution. Some material melts during this process, the shock heating raising temperatures above the solidus. other material remains solid but shocked, its crystal structure permanently altered by the passage of extreme pressures. The melt volume represents a significant fraction of the excavated material. For an impact of this magnitude, perhaps 10% of the excavated rock reaches temperatures sufficient for melting. This melt, a mixture of target rock and vaporized impactor, collects in pools at the crater bottom or becomes entrained in the ejecta, forming glassy spherules that cool during ballistic flight. These impact spherules, when they eventually settle to the surface, create a globally distributed layer marking the impact event in the geological record. Shocked quartz appears throughout the ejecta, diagnostic evidence of impact. Normal geological processes cannot produce the characteristic planar deformation, features microscopic parallel fractures within quartz crystals that form only under shock pressures exceeding 5 gigapascals. These features develop in microseconds as the shockwave passes through the crystal lattice, creating permanent deformation that persists after pressure release. Geologists searching for ancient impact sites look for shocked quartz as confirmatory evidence, the mineral signature that separates impact structures from volcanic calderas or other circular geological features. The crater modification phase begins even before excavation completes. The transient crater exceeds the gravitational stability limit for rock at this scale. The walls, initially nearly vertical, begin to collapse inward under their own weight. The collapse occurs as a series of massive landslides, terrace-forming slumps that create the stepped wall profile characteristic of complex craters. Each terrace represents a failure surface where rock lost coherence and flowed downward, accumulating as jumbled blocks on the crater floor. The central uplift rises from the crater floor, driven by elastic rebound of compressed rock beneath the impact site. This uplift brings deep crustal material to the surface, exposing rock that formed tens of kilometers below ground under high temperature and pressure conditions. The uplift rises several kilometers before collapsing back partially, forming either a central peak or, for larger craters, a peak ring, a circular mountain range surrounding a flat inner basin. The Chicxulub crater displays a peak ring, visible in gravitational data though buried beneath younger sediment. The final crater diameter stabilizes at roughly 100 kilometers, twice the transient crater width. The crater depth, measured from rim to floor, reaches perhaps 5 kilometers, though the true structural depth, the distance from the original surface to the deepest shocked rock, extends much deeper. The crater represents a profound disturbance to the crust, a puncture wound that exposes geological history and creates new topography that will influence drainage patterns and erosion for millions of years. Seismic energy radiates outward through the crust and mantle. The impact generates the equivalent of a magnitude 10.5 earthquake, though the concept strains at such energy levels. Traditional earthquakes release energy accumulated gradually through tectonic stress, propagating from fault ruptures that extend over seconds to minutes. Impact earthquakes release energy instantaneously from a point source, creating seismic wave patterns that differ from tectonic events. The differences allow seismologists to distinguish impact-generated earthquakes in the geological record, identifying ancient impacts that left no visible crater. Surface waves propagate around the planet, circling multiple times before dissipating. These waves, similar to ripples on a pond but traveling through solid rock, reach peak-to-peak amplitudes of several meters near the impact site, decreasing to centimeters at antipodal distances. Buildings sway violently, bridges oscillate, anything freestanding falls. The shaking continues for minutes. Not the brief jolts of typical earthquakes, but sustained ground motion that liquefies saturated soils and triggers landslides on unstable slopes. The antipodal point experiences focused seismic energy, waves that have travelled through the planet and converged on the opposite side. Some models suggest this focusing could trigger volcanism, fracturing the crust and allowing magma to reach the surface more easily. The Siberian traps flood basalts, which erupted around the time of the Permian-Triassic extinction event, have been speculatively linked to the Wilkes-Land impact in Antarctica, though the evidence remains controversial and the mechanism uncertain. More certain are the immediate effects on existing volcanic systems. Seismic waves passing through magma chambers disturb the pressure equilibrium, potentially triggering eruptions from volcanoes already near critical conditions. Stratovolcanoes worldwide might experience flank collapse, explosive eruptions, or lava outpouring in response to seismic shaking. The additional volcanic aerosols compound atmospheric effects from the impact itself, adding sulfur dioxide and ash to the stratosphere. The crater cools slowly. The impact melt sheet, potentially hundreds of meters thick, takes decades to fully solidify. Hydrothermal systems develop as groundwater encounters hot rock, creating geysers and hot springs around the crater rim. These hydrothermal systems mobilize metals and minerals, depositing them in veins and fractures, creating ore bodies that future geologists, if any survive, might mine. Impact structures often host mineral deposits. The shock metamorphism and hydrothermal activity concentrating economically valuable elements. The crater becomes a basin, a depression that accumulates sediment and water. Lakes form in the low areas, their water chemistry altered by contact with shocked and melted rock. These impact crater lakes sometimes develop unusual ecosystems, though in this case, the broader environmental catastrophe prevents any immediate biological colonization. Only took seconds to excavate what erosion would require millions of years to accomplish. The universe prefers efficiency, apparently, even when that efficiency manifests as violence. Rock remembers pressure and temperature, carries the memory and altered crystals and melted minerals. The sky transforms within hours of impact. Material ejected at velocities exceeding escape speed leaves Earth entirely, though most will eventually return, falling back over days and weeks. Material launched at intermediate velocities follows ballistic trajectories, arcing through the upper atmosphere before descending thousands of kilometers from the impact site. The fastest suborbital ejector reaches altitudes above 100 kilometers, technically entering space before falling back. This material glows during re-entry, each fragment a miniature meteor, millions of them simultaneously, creating a spectacle visible across an entire hemisphere. The collective re-entry of ejecta delivers thermal energy to the atmosphere on a global scale. Each returning fragment heats the air it passes through, converting residual kinetic energy into thermal radiation. Individually, fragments are small, but collectively they number in the billions, distributed across millions of square kilometers of atmosphere. The integrated thermal flux reaches levels sufficient to ignite vegetation on a continental scale. Forests that survived the initial impact, shielded by distance or topography, face a second assault from above as thermal radiation from re-entering ejecta bathes the landscape in radiant heat. Models of the Chicxulub impact suggest this. Ejecta re-entry thermal pulse may have been more devastating to ecosystems than the impact itself. The pulse lasted perhaps an hour, sustained infrared radiation at intensities comparable to being inside an oven set to broil. Small animals could find shelter underground or underwater, but large animals, especially those in open environments, faced unsurvivable conditions. Forests ignited en masse, creating firestorms that merged into continental-scale conflagrations. The same physics applies to a 3I Atlas impact. The thermal pulse from re-entry begins within an hour of impact and continues for several hours as progressively slower. Lower trajectory ejecta returns. The intensity varies with location regions directly downrange from the impact receive more ejecta and experience higher thermal flux. Regions on the opposite hemisphere receive less direct ejecta, but still experience significant heating from material distributed globally by atmospheric circulation. Smoke from ignited vegetation rises into the atmosphere, forming pyrocumulus clouds that dwarf any wildfire smoke plumes in recorded history. These clouds reach into the stratosphere, injecting soot particles that will remain aloft for months or years. The soot joins other atmospheric contaminants rock dust from the ejecta blanket, sulfur aerosols from vaporized sulfate minerals, water vapor from vaporized ocean or groundwater. Together, these materials begin to block incoming solar radiation. The optical depth of the atmosphere increases dramatically. Within days, sunlight reaching the surface drops to a fraction of normal levels. The sky, when visible through the dust and soot, appears reddish-brown rather than blue, the colour of a perpetual sunset as shorter wavelengths scatter preferentially, while longer wavelengths penetrate. Temperatures at the surface begin to drop, despite the initial thermal pulse, as the energy balance shifts toward outgoing thermal radiation with diminished solar input. This twilight persists. Dust particles in the stratosphere have residence times measured in months to years, depending on particle size and altitude. The finest particles, sub-micron aerosols, remain aloft longest, spreading globally through stratospheric circulation patterns. Coarser dust settles more quickly, but still takes weeks to months to clear completely. The atmospheric clearing happens gradually, a slow brightening that offers no single moment of return to normal conditions. Photosynthesis ceases wherever light levels drop below the compensation point, the threshold where photosynthetic production equals respiratory consumption. Different plant species have different compensation points, but most terrestrial plants require at least 1% of full sunlight to sustain growth. When light levels drop below this threshold, plants begin to starve, metabolizing their own tissues to maintain basic cellular functions. Small plants with limited energy reserves die within weeks. Larger plants, particularly trees with substantial stored carbohydrates, can survive months in darkness, entering dormancy and waiting for light's return. But months exceed the survival time for most herbivores. Without fresh vegetation, herbivorous animals deplete available food supplies quickly. Decomposing plant material offers some nutrition, but without new growth, the resource base collapses. Small herbivores die first, their higher metabolic rates demanding constant food intake. Large herbivores follow within weeks to months, their greater body mass providing some buffer but ultimately insufficient. Starvation proceeds from the smallest to the largest, a cascade of mortality that moves up the size spectrum. Carnivores face initial abundance as herbivores die, providing carrion in unprecedented quantities. Scavengers thrive briefly, but the resource proves temporary. Once herbivore populations collapse, carnivores lose their prey base and begin starving as well. The ecosystem unravels from bottom to top, primary producers failing first, then primary consumers, then secondary consumers, each trophic level collapsing in sequence. Marine ecosystems follow similar trajectories. Phytoplankton, the photosynthetic organisms that form the base of oceanic food webs, require light in the upper water column. When atmospheric dust blocks sunlight, phytoplankton productivity drops precipitously. Some species enter dormancy, forming resting spores that can survive months to years of darkness. Others simply die, their populations crashing within weeks. Zooplankton, the small animals that graze on phytoplankton, deplete the remaining primary production quickly and begin starving. Fish that depend on zooplankton face food shortages within weeks. Larger predatory fish initially benefit from smaller fish dying and providing carrion, but the resource collapses as populations crash. Oceanic ecosystems show some resilience compared to terrestrial systems. Deep ocean communities that depend on chemosynthesis rather than photosynthesis remain unaffected by surface light levels. Hydrothermal vent communities, sustained by chemical energy from Earth's interior rather than solar energy, persist through the impact winter unchanged. These communities offer refugia where life continues, isolated pockets of biological activity in an otherwise quiescent ocean. The impact winter represents a planetary-scale disruption to the energy budget. Earth's climate system depends on solar input, with energy flowing from the sun to the surface, driving weather patterns, ocean currents, and biological activity. When solar input drops by 90% or more, the entire system reorganizes around diminished energy availability. Temperatures drop globally. ice sheets begin advancing from polar regions. Precipitation patterns shift as reduced evaporation limits atmospheric moisture. The term impact winter parallels nuclear winter, the hypothetical climatic consequence of large-scale nuclear warfare. Both scenarios involve stratospheric aerosols blocking sunlight and causing surface cooling. The mechanisms differ in detail. Nuclear winter invokes soot from burning cities. Impact winter invokes dust from vaporized rock, but the atmospheric physics remain similar. Both scenarios rely on particles in the stratosphere, above the weather layer, where they persist without being rained out. How long the impact winter persists depends on particle characteristics and stratospheric circulation. Models suggest 1 to 3 years of severe light reduction, followed by gradual recovery over an additional 2 to 5 years. During the first year, temperatures might drop 10 to 20 degrees Celsius globally, more at high latitudes, less near the equator. Ice and snow coverage increases, creating positive feedback as reflective surfaces return more of the diminished sunlight to space. Ocean surface temperatures drop, though the ocean's thermal inertia moderates cooling relative to land surfaces. Only took hours for 1 billion years of photosynthetic evolution to become temporarily irrelevant. Life spent eons optimizing for solar energy capture, and then, briefly, darkness. The planet adjusts its energy budget downward, waiting for atmospheric clearing that comes slowly, if at all. The thermal pulse arrives as a wave of infrared radiation that transforms landscapes within minutes. Material ejected from the impact crater re-enters the atmosphere at speed sufficient to heat the air to incandescence. This heated air radiates energy across the electromagnetic spectrum. With peak emission in the infrared, the radiation travels at light speed, bathing the surface before physical ejecta arrives, before sound arrives, before any mechanical effect reaches beyond the immediate impact zone. Vegetation ignites first. Leaves and needles, with their high surface area to volume ratios, absorb thermal radiation efficiently and reach ignition temperature within seconds. Grasses char and burst into flame. Forest canopies erupt in fire that spreads laterally through crowns faster than fire can propagate along the ground. The ignition is nearly simultaneous across vast areas, not a single fire spreading from a point source, but spontaneous combustion, occurring wherever thermal flux exceeds the ignition threshold and sufficient oxygen is present. The intensity varies with distance from the impact site and with line of sight to the re-entering ejecta. Regions within direct view of the ejecta curtain experience the highest thermal flux, perhaps several kilowatts per square meter, sustained over tens of minutes. This intensity exceeds that of direct sunlight by factors of 10 or more. Materials that would never ignite under normal solar heating begin to smolder and burn. Synthetic materials melt, paint blisters, wood surfaces blacken and ignite. Beyond the horizon from the impact site, the thermal pulse diminishes but remains significant. Ejecta re-entering over distant regions still radiates heat, though at lower intensities. The radiation arrives from overhead rather than from a concentrated source, creating diffuse heating across the sky. This diffuse heating may not ignite vegetation directly, but raises surface temperatures substantially, desiccating fuels and preparing them for ignition from secondary sources, lightning from pyrocumulus clouds, embers carried by wind. Spontaneous combustion as dried organic matter reaches auto-ignition temperatures. Firestorms develop where conditions favour their formation. A firestorm requires not just ignition, but sustained combustion with sufficient heat release to create powerful updrafts. The updrafts pull in surrounding air, creating winds that feed the fire with oxygen and carry embers outward, igniting new areas. The fire becomes self-sustaining, generating its own weather patterns, creating convection columns that reach into the stratosphere. These columns loft smoke and ash to altitudes where particles remain airborne for months, contributing to the atmospheric darkening that follows. Not all ignited vegetation produces firestorms. In many areas, fires burn without developing the organized convection patterns that characterize firestorms. These fires consume available fuel and spread according to wind and topography, behaving like large-scale versions of natural wildfires. They burn until fuel is exhausted or until conditions change rain, if any falls, or simple lack of combustible material in areas where vegetation is sparse. Water provides some protection. Lakes and rivers shield aquatic organisms from direct thermal effects, though the water surface itself heats and may experience localized boiling where thermal flux is highest. Organisms beneath the water surface remain buffered from thermal radiation by the water's high heat capacity and opacity to infrared. Fish survive the thermal pulse, though they face subsequent challenges as ash and debris settle into water bodies, reducing oxygen levels and altering water chemistry. Underground spaces offer complete protection from thermal radiation. Animals in burrows, caves, or crevices experience no direct effects from the thermal pulse. The rock and soil above them absorb and dissipate heat without transferring significant energy to the sheltered spaces. These refugia become critical for survival organisms that can access underground environments, avoid the thermal effects that devastate surface populations. The pulse duration matters as much as intensity. A brief thermal spike allows materials to dissipate heat through conduction and radiation before temperatures rise to damaging levels. A sustained pulse overwhelms these cooling mechanisms, driving temperature steadily upward until ignition or thermal decomposition occurs. The ejector re-entry pulse lasts between 30 minutes and 2 hours, depending on location and the distribution of returning material. This duration proves sufficient to ignite most combustible materials in exposed areas. Human structures fare poorly. Buildings made of wood ignite and burn. Concrete and masonry structures survive the thermal pulse structurally, but may experience surface spalling as rapid heating creates steam in pores and microcracks, leading to explosive failure of surface layers. Metal roofs and siding heat to temperatures that ignite interior contents through radiant heat transfer. Glass windows fail, either shattering from thermal stress or simply transmitting enough heat to ignite interior furnishings. Urban areas become particularly hazardous. The concentration of combustible materials and structures creates fuel loading far exceeding natural ecosystems. When ignition occurs, the fire spreads rapidly through interconnected buildings, creating conflagrations that merge into citywide firestorms. These urban firestorms generate extreme heat and consume oxygen so rapidly that survival becomes impossible, even in nominally fire-resistant buildings. Carbon monoxide and smoke fill the air, creating toxic atmospheres that extend well beyond the actual flame fronts. The smoke itself becomes a global phenomenon. Soot particles, composed primarily of black carbon from incomplete combustion, rise into the atmosphere through pyroconvective processes. These particles absorb solar radiation efficiently, heating the surrounding air and creating additional convection that lofts them higher. Once in the stratosphere, the soot spreads globally, adding to the dust already present from the impact itself. The combined effect of dust and soot creates an atmospheric burden unprecedented in human experience. The optical depth increases by orders of magnitude over pre-impact conditions. Light transmission drops to single-digit percentages. The surface environment transitions from illuminated to dim twilight, a perpetual dusk that persists regardless of the sun's position in the sky. Diurnal temperature variations diminish without significant solar heating during the day. Temperatures remain relatively constant, a constant cold that reflects outgoing thermal radiation, without replacement from incoming solar energy. Photosynthetic organisms, evolved over billions of years to capture solar energy, find themselves in an environment where that energy has vanished. Their biochemical machinery, tuned to absorb specific wavelengths of visible light, receives insufficient photons to drive carbon fixation. The organism's metabolic balance shifts from net production to net consumption, drawing down internal energy reserves to maintain cellular processes. Without new energy input, these reserves deplete over days to weeks, and the organism enters dormancy or dies. The ecological collapse follows predictably from energy limitation. Ecosystems are fundamentally systems for capturing, transforming and transferring energy. Remove the primary energy input and the system disintegrates. The biomass present at the time of impact represents stored energy, a finite resource that organisms can exploit temporarily, but which cannot sustain populations indefinitely. Decomposers briefly flourish as dead organic matter accumulates, but they too face ultimate limitation as the resource depletes and new production ceases. Only took minutes for thermal radiation to ignite a hemisphere. Fire represents rapid oxidation, energy release, chemistry operating at its most exothermic. The planet burns, then cools, then goes dark. Energy flows downward toward equilibrium, toward stillness. The oceans respond to impact with their own category of catastrophe. If 3I Atlas strikes water rather than land, the immediate crater excavation displaces millions of cubic kilometers of seawater, pushing it outward in all directions simultaneously. The displaced water forms a cylindrical cavity, a momentary hole in the ocean floor that exposes bedrock beneath. This cavity persists for seconds only before collapsing inward, gravity pulling water back toward the impact site in a massive converging flow. The collapsing cavity creates a central water column that rises hundreds of meters above mean sea level, a temporary mountain of water driven upward by the convergence of the collapsing rim. This central peak rises, reaches maximum height, then collapses back down, creating a series of concentric waves that propagate outward from the impact site. These waves constitute the tsunami, though the term fails to capture the scale of the phenomenon. Normal tsunamis, generated by submarine earthquakes or landslides, carry wavelengths of hundreds of kilometers and amplitudes of meters. Impact-generated tsunamis carry similar wavelengths, but amplitudes measured in hundreds of meters near the source. The waves travel outward at speeds determined by water depth. In deep ocean, tsunami velocity approaches 800 kilometers per hour, comparable to jet aircraft. The waves pass ships unnoticed, their amplitude negligible in deep water despite enormous energy content. The wave energy distributes vertically through the entire water column, making tsunamis invisible from the surface until they approach shallow water, and shoaling effects concentrate energy into amplitude. As the waves approach coastlines, the decreasing water depth forces energy upward. The wave slows but grows taller, its amplitude increasing as wavelength decreases. The leading edge of the wave reaches shallow water first, slowing while the trailing edge continues at higher velocity, causing the wave to steepen. Eventually the wave becomes unstable, the front face too steep for water to maintain coherent flow, and the wave breaks, becoming a turbulent bore that rushes inland. The run-up height, the maximum elevation above sea level that water reaches, depends on coastal topography and wave amplitude. For an impact-generated tsunami originating mid-ocean, run-up heights at distant coastlines might reach 50 to 100 meters, potentially more in locations where bathymetry focuses wave energy. These heights exceed any tsunami in recorded history by factors of 5 to 10. Water reaches elevations far above normal coastal flooding, inundating areas thought safe, overtopping coastal defences designed for conventional scenarios. The inundation extends kilometres inland, depending on topography. Flat coastal plains allow water to penetrate tens of kilometres from the shoreline, creating temporary seas where land existed minutes before. Steep coastal topography limits inland penetration, but concentrates wave energy, creating higher run-up but narrower inundation zones. Valleys oriented perpendicular to the coast funnel water inland, amplifying inundation distance. Valleys oriented parallel to the coast experience less severe effects. The water carries debris, both natural and human-made, trees, soil, buildings, vehicles, ships. Anything not firmly attached to bedrock becomes entrained in the flow and transported inland. This debris adds momentum and destructive power to the water, turning the tsunami into a slurry of water and solid objects that demolishes structures through impact and abrasion rather than pressure alone. The debris field, when water eventually recedes, covers the coastal zone with chaotic mixtures of material from ocean and land, marine sediment mixed with terrestrial soil, oceanic organisms stranded among terrestrial vegetation. The backwash, the return flow as water drains back to sea, carries additional material seaward. Buildings weakened by the initial inundation collapse during backwash, their foundations undermined, their structures battered from both directions. The return flow transports sediment and debris into the ocean, depositing it on the continental shelf and slope, creating turbidity currents that travel down submarine canyons and deposit material in deep ocean basins. The geological record of the tsunami persists as an anomalous sediment layer, a mixture of terrestrial and marine material deposited far from typical sources. Multiple waves follow the initial impact. The oscillating water surface creates a wave train, a series of tsunami waves separated by periods of 30 minutes to several hours. The waves arrive with diminishing amplitude, each smaller than the previous, but even secondary and tertiary waves carry sufficient energy to cause significant damage. The wave train continues for hours, making immediate coastal reoccupation dangerous even after the first wave recedes. Ocean basins act as resonators, sustaining oscillations for days after impact. The natural frequencies of ocean basins, determined by their dimensions and depths, match certain periods in the tsunami wave spectrum, leading to amplification and prolonged oscillations. These oscillations are called seisures, manifest as rhythmic sea level variations that persist long after the initial tsunami energy dissipates. Harbours and bays experience particularly strong seisures, their smaller volumes and restricted connections to the open ocean creating resonance conditions. Marine ecosystems face wholesale disruption. Coastal habitats, coral reefs, kelp forests, seagrass beds experience physical destruction from wave energy and sediment transport. Coral colonies break and scatter. Kelp fronds shred and drift. Seagrass uproots and deposits in chaotic mats. The organisms inhabiting these ecosystems face mortality from mechanical damage and habitat loss. Those that survive find their environment transformed. Familiar structures replaced by rubble and sediment. Offshore ecosystems experience less direct damage, but face altered conditions as sediment settles from the water column. Fine sediment remains suspended for weeks, reducing light penetration and interfering with filter-feeding organisms. The sediment eventually settles, creating a blanket that covers the seafloor and buries benthic organisms. Some species can migrate vertically through thin sediment layers, but thick deposits smother and kill in faunal communities. The impact injects large quantities of vaporized rock and water into the atmosphere, some of which eventually returns to the ocean as acidic precipitation. The vaporized rock contains sulfur compounds that form sulfuric acid in the atmosphere, while nitrogen oxides form from atmospheric heating during impact. These acids dissolve in precipitation and fall as acid rain, lowering ocean surface pH and creating stress for calcifying organisms like corals, mollusks, and planktonic foraminifera. Ocean chemistry shifts globally over weeks to months as impact-derived compounds mix through surface waters. The pH changes, the particulate loading, the altered light regime all stress marine life adapted to relatively stable conditions. Some species tolerate the changes, others decline precipitously. The ecosystem reorganizes around new conditions, communities restructuring as tolerant species expand and sensitive species contract. Coastal human populations face annihilation within the tsunami inundation zone. No warning system provides adequate evacuation time. The waves arrive hours after impact, but the impact itself creates conditions that prevent effective communication and evacuation. Power failures, destroyed infrastructure, ongoing fires, and atmospheric effects impede organized response. Most coastal inhabitants remain unaware of the approaching tsunami until it arrives. only took hours for water to travel across an ocean basin. Gravity and momentum move water efficiently, requiring no energy input beyond the initial displacement. The ocean sloshes, returns to equilibrium, leaves shorelines rearranged and emptied of life. The ecological collapse proceeds from the foundation upward. A systematic dismantling of energy flow through food webs. Primary producers, plants, algae, photosynthetic bacteria constitute the base of nearly all terrestrial and aquatic ecosystems. These organisms capture solar energy and convert it to chemical energy stored in organic compounds. Everything else, from herbivorous insects to apex predators, depends ultimately on this primary production. When sunlight vanishes beneath stratospheric dust and soot, primary production ceases, and the entire edifice begins to crumble. The timeline of collapse varies by organism size, metabolic rate, and stored energy reserves. Small organisms with high metabolic rates exhaust their resources quickly. Insects, with their large surface area to volume ratios and rapid metabolism, require constant food intake to maintain body temperature and activity. When vegetation dies and stops producing new foliage, herbivorous insects deplete available resources within days. Their populations crash first, a wave of mortality that spreads through insect communities globally within the first week after impact. Larger herbivores last longer but face inevitable decline. Small mammals, rodents, rabbits, small marsupials survive weeks on stored seeds, remaining vegetation, and scavenged material. But reproduction ceases when food becomes scarce, and without reproduction, populations decline through attrition even if adults survive temporarily. Large herbivores, megafauna with body masses exceeding several hundred kilograms, carry sufficient internal energy reserves to survive months, but they cannot reproduce, cannot maintain populations through a multi-year impact winter. Birds face particular challenges. Flight requires high metabolic rates, and maintaining body temperature in cooling climates demands constant energy input. Migratory species find their destinations altered or destroyed, familiar habitats buried under ash or burned to bare ground. Seed-eating birds fare slightly better than insectivores, as seeds remain viable and available longer than living insects. But seed banks deplete over months, and without new plant growth, seed-eating species eventually face starvation as well. Aquatic ecosystems show different trajectories. Freshwater systems, particularly those fed by groundwater rather than surface runoff, maintain some stability initially. Cold water fish tolerate the cooling climate better than terrestrial organisms tolerate loss of vegetation. But as detritus from dead terrestrial vegetation washes into streams and lakes, decomposition consumes dissolved oxygen, creating hypoxic or anoxic conditions that kill fish and other aquatic organisms. The aquatic ecosystem shift from limitation by food availability to limitation by oxygen availability. Marine ecosystems stratified by depth. Surface waters, dependent on phytoplankton and sunlight, collapse rapidly as light penetration drops below photosynthetic thresholds. Midwater ecosystems, dependent on organic matter sinking from surface production, face delayed collapse as the supply of sinking particles diminishes over weeks to months. Deep-sea ecosystems, already adapted to low-energy input, experience the least disruption initially, though even they face eventual resource limitation as surface production, which ultimately supports them, ceases. The exceptions cluster around chemosynthetic communities, hydrothermal vent ecosystems, powered by chemical energy from Earth's interior rather than solar energy, continue functioning through the impact winter unaffected. Tube worms, vent crabs, and chemosynthetic bacteria persist, their ecosystem sustained by hydrogen sulfide and other reduced compounds emerging from the crust. These communities represent islands of biological activity in an otherwise quiescent ocean, refugia where energy flow continues despite surface catastrophe. Cold seeps, locations where methane and hydrogen sulfide percolate through seafloor sediments. support similar chemosynthetic communities. These ecosystems remain equally unaffected by surface-like conditions, though changes in ocean chemistry or temperature might influence them indirectly. The chemosynthetic ecosystems inherit the ocean, becoming the dominant productive systems during the impact winter, a reversal of their normal marginal status. Scavengers experience a brief golden age. Dead organisms accumulate faster than decomposition can process them, creating abundant carrion resources. Carrion beetles, vultures, hyenas, and other specialist scavengers find food plentiful, at least initially, but the resource proves finite. Once herbivore populations collapse, carnivores die, and the wave of mortality passes through large animals. The supply of fresh carrion diminishes. Scavengers face the same ultimate energy limitation as every other consumer without primary production to generate new organic matter. The system exhausts its stored energy, decomposes bacteria, fungi. Invertebrate detritivores dominate temporarily as dead organic matter accumulates. Microbial respiration increases, processing the necromass into simpler compounds. But decomposition requires oxygen, and in environments where dead material accumulates thickly, oxygen depletion limits decomposition rates. Anoxic conditions develop in soils with high organic content, in lake sediments, in ocean waters. The decomposition stalls, and organic matter accumulates in partially decomposed states. This accumulated organic matter represents a carbon store, biomass that would normally cycle through ecosystems, but instead becomes buried under sediment or ash. Some of this material, if buried deeply enough and subjected to appropriate pressure and temperature conditions over millions of years, might eventually become coal or oil, fossilized remnants of the impact winter's mass mortality. The impact creates future fossil fuels from organisms it killed, an irony measured in geological time. Plant survival depends on dormancy mechanisms. Seeds, spores, and underground storage organs can survive years of darkness, waiting for conditions to improve. Many plant species evolve these survival strategies for seasonal dormancy, for surviving winter or dry seasons. The impact winter represents an extreme version of seasonal dormancy, longer and more severe, but not fundamentally different in kind. Seeds buried in soil remain viable for years, protected from temperature extremes and mechanical damage. When light eventually returns, these dormant propagules germinate, recolonizing barren landscapes slowly. The initial plant communities resemble early successional assemblages, fast-growing, opportunistic species that exploit disturbed environments over decades and centuries. These pioneer communities give way to more complex ecosystems as slower-growing, competitive species establish. The recovery timeline extends to millennia for full ecosystem restoration to pre-impact complexity. Animal survival depends on access to refugia caves, deep burrows, underwater habitats, any location buffered from extreme conditions. Small mammals in burrows survive the thermal pulse, the impact winter, the food scarcity. They emerge periodically to forage on seeds, fungi, and remaining organic matter. Their populations decline but persist at low levels, sustained by scavenging and the slow decomposition of pre-impact biomass. Amphibians and reptiles, with their lower metabolic rates and ability to enter torpor, survive better than birds and mammals. They can reduce energy expenditure to minimal levels, waiting out the impact winter in dormant states. Their cold-blooded physiology, often considered less advanced than warm-blooded metabolism, becomes advantageous when energy is scarce and temperatures drop. They inherit the post-impact world, at least temporarily, until ecosystems rebuild and endothermic lineages recover. Only took weeks for ecosystems to collapse that took millions of years to assemble. Energy limitation simplifies everything, reduces complex food webs to scattered survivors waiting in darkness. The planet holds its breath, metabolically speaking, burning through stored reserves while waiting for the sun's return. The long freeze settles over the planet as months extend into years without significant solar heating. Atmospheric dust and soot persist in the stratosphere, their residence time determined by gravitational settling rates and stratospheric circulation patterns. The finest particles, submicron aerosols, remain aloft longest, creating a persistent veil that blocks 60 to 90% of incoming sunlight. Surface temperatures respond to the new energy balance, dropping steadily as thermal radiation to space continues, while solar input diminishes to negligible levels. The cooling proceeds faster over land than ocean. Continental interiors, far from the moderating influence of large water bodies, experience temperature drops of 20 to 30 degrees Celsius within the first year. Winter temperatures in mid-latitudes reach values typically associated with polar regions. Summer temperatures, without sufficient solar heating, fail to rise significantly above winter levels. The seasonal cycle dampens, replaced by a permanent cold that varies little throughout the year. Ice sheets begin advancing from polar regions and high-altitude areas where glaciers persisted before impact. The ice growth follows established physical principles. Accumulation exceeds ablation when temperatures remain below freezing year-round, and some precipitation continues. The ice sheets advance slowly, meters to tens of meters per year, flowing downslope under their own weight, scouring underlying rock and soil. The advance continues as long as the impact winter persists, potentially covering millions of square kilometers in ice within decades. Sea ice expands from the poles, covering increasingly large fractions of the ocean's surface. The ice reflects incoming sunlight efficiently, creating positive feedback. More ice leads to higher albedo, which leads to more cooling, which leads to more ice. This ice albedo feedback accelerates cooling in high latitudes, potentially triggering runaway glaciation if conditions persist long enough. The tropical oceans remain ice-free, their warmer initial temperatures and continued heat transport from depth preventing surface freezing. Ocean circulation patterns reorganize around the new temperature distribution. Thermohaline circulation, driven by density differences related to temperature and salinity, weakens as surface waters cool globally. The reduced circulation slows heat transport from tropical to polar regions, allowing polar cooling to intensify further. The ocean stratifies more strongly, with cold surface waters overlying warmer deep waters and reduced mixing between layers. This stratification affects oxygen distribution, potentially creating expanding oxygen minimum zones at intermediate depths. Precipitation decreases globally as cooling reduces evaporation rates. Less water vapor enters the atmosphere, and what does enter tends to precipitate closer to moisture sources rather than being transported long distances. Continental interiors become particularly dry, receiving minimal precipitation and developing desert-like conditions despite low temperatures. The cold, dry climate resembles glacial periods in Earth's paleoclimate record, episodes when ice sheets covered much of North America and Europe, and global climate shifted toward aridity. The regions that remain hospitable to life contract toward the equator and specific microclimates. Geothermal areas, hot springs, volcanic regions, locations where heat from Earth's interior reaches the surface become biological refugia. These areas maintain temperatures above freezing despite the global freeze, and the available thermal energy supports small ecosystems. Thermophilic bacteria thrive in hot springs. Heat-tolerant plants grow near thermal vents. Animals congregate around these warmth sources, creating population concentrations in areas that were marginal before impact. Deep-sea hydrothermal vents continue supporting their chemosynthetic communities, unaffected by surface temperature changes. The vents represent stability in a changing world, their energy source independent of solar input or atmospheric conditions. The vent communities persist as they have for hundreds of millions of years, indifferent to catastrophes above. If complex life survives the impact winter anywhere, the vents seem likely candidates, isolated but sustainable. Caves offer another category of refuge. Deep caves maintain relatively constant temperatures year-round, buffered by surrounding rock from surface temperature fluctuations. Cave temperatures typically approximate the mean annual surface temperature of the region, which drops during impact winter, but remains above the extreme cold of the surface during winter months. Cave ecosystems, adapted to darkness and limited food input, continue functioning much as they did before impact. Cave-adapted species, already specialized for low-energy environments, face minimal additional stress. Subterranean environments more generally provide insulation from surface extremes. Organisms living in soil, in groundwater, in fractured bedrock exist in relatively stable thermal environments. Soil temperature at depths below a few meters varies little throughout the year, remaining near the mean annual surface temperature. As that mean drops during impact winter, deep soil cools but avoids the extreme temperature swings of the surface. Microorganisms, invertebrates, and small vertebrates in these environments survive more readily than surface-dwelling organisms. The biosphere contracts to these refugia, abandoning vast areas that become effectively sterile. The surface of continents outside equatorial regions becomes barren, windswept, scoured by occasional storms but mostly still under high-pressure systems that dominate cold, dry climates. Dust storms occasionally mobilize fine sediment, transporting it across continents and depositing it in layers that will mark this interval in the geological record. The dust consists of impact ejecta mixed with soil particles, forming a distinctive sedimentary unit that future geologists might identify as an impact marker. Ice cores drilled from ice sheets that eventually form during the impact winter preserve atmospheric composition during this period. The cores would show elevated levels of iridium and other platinum group elements, signatures of the impactor mixed into global dust. They would show high levels of soot from global wildfires. They would show altered isotopic ratios reflecting disrupted biological cycles. These chemical and isotopic anomalies would appear as a sharp boundary in the ice core record, marking the year of impact as clearly as tree rings mark exceptional years. Life persists in diminished form, scattered across marginal habitats, waiting for conditions to improve. The waiting extends beyond individual lifespans, beyond generations, becoming an evolutionary filter that selects for traits enabling survival in extreme low-energy environments. Organisms with low metabolic rates, efficient energy use, tolerance for cold, ability to enter dormancy. These traits become adaptive during impact winter, favored by selection because they enable survival when most other organisms perish. The planet itself remains largely indifferent to the biological catastrophe. Geological processes continue operating at their usual rates. Plate tectonics proceeds. Continents drift. Mountains erode. Sediments accumulate. The impact represents a perturbation, significant on biological timescales, but minor on geological ones. In the stratigraphic record, the impact appears as a thin layer, a boundary marking the transition from one geological moment to the next. Below the boundary, fossils of pre-impact organisms. Above the boundary, a gap. Then eventually fossils of post-impact survivors and their descendants. Only took a few years for temperatures to drop to levels typical of ice ages. The planet knows how to be cold, has been cold before, will be cold again. The warmth of the Holocene, the interglacial period in which human civilization developed, represents an anomaly, a brief thaw in a generally frigid system. Impact winter simply accelerates the transition back to cold, collapses it from millennia into years. What survives does so through improbable combinations of location, physiology, and chance. The survivors cluster in environments that offer at least one critical resource-stable temperature, accessible food, liquid water, oxygen, shelter from radiation or mechanical stress. No single location provides all necessities optimally, forcing trade-offs. Organisms surviving in one refuge face different challenges than those surviving in another, leading to divergent selective pressures and the possibility of evolutionary divergence among isolated populations. Microbial life demonstrates the greatest resilience. Bacteria and archaea, with their metabolic diversity and rapid reproduction, exploit resources unavailable to multicellular organisms. Psychrophilic bacteria thrive in ice, growing slowly at temperatures well below freezing. Thermophilic bacteria colonize hot springs and hydrothermal systems. Chemolitho-autotrophs derive energy from inorganic chemical reactions, oxidizing hydrogen sulfide, methane, ferrous iron, or other reduced compounds. These metabolic strategies, marginal in pre-impact ecosystems dominated by photosynthesis, become dominant during impact winter when light disappears. Endolithic microorganisms, those living within rock, persist largely unaffected. They inhabit pore spaces in sandstone, fractures in granite, vesicles in basalt, extracting nutrients from mineral surfaces and atmospheric gases that diffuse into the rock. Their growth rates, already slow before impact, remain unchanged. The rock provides stable temperatures, protection from ultraviolet radiation and mechanical disturbance, and sufficient moisture from atmospheric humidity. Endolithic communities continue their cryptic existence, invisibly maintaining Earth's microbial diversity through the crisis. Fungal networks survive in soil and wood, their mycelia threading through substrate and waiting for conditions to improve. Fungi metabolize dead organic matter, requiring no light, tolerating cold, and growing slowly on limited resources. The accumulated necromass from impact-killed organisms provides substrate for fungal growth during the impact winter. Fungal spores, resistant to temperature extremes and desiccation, remain viable for years or decades, germinating when moisture and substrate become available. Seeds and spores represent biological time capsules, packages of genetic information and stored energy designed to wait. Their dormancy mechanisms evolve for seasonal or episodic challenges, winter, drought, fire, but function adequately for impact winter's extended duration. Some seeds require cold stratification to break dormancy, a mechanism ensuring germination occurs in spring. These seeds wait through the impact winter, chemically registering the prolonged cold, and germinate when temperatures eventually rise and light returns. Deep soil seed banks contain thousands of seeds per square meter, accumulated over decades or centuries. Not all species produce long-lived seeds, but enough do that soil seed banks provide a reservoir of genetic diversity awaiting favourable conditions. The seeds buried deepest, protected by overlying soil from temperature fluctuations and mechanical disturbance, survive best. When ecosystems eventually recover, these seeds contribute to plant community reassembly. Though the process takes decades to centuries, small mammals in burrow complexes survive through a combination of torpor, cached food, and opportunistic foraging. Species that evolve for seasonal hibernation can extend dormancy periods, reducing metabolic rates to minimal levels and surviving months on stored fat. Between torpor bouts, they forage on seeds, fungi, and any remaining organic matter. Their populations decline sharply, but some individuals persist in favourable locations, maintaining genetic lineages through the bottleneck. Aquatic organisms face different constraints. Fish in deep lakes or ocean depths survive where temperatures remain stable and oxygen persists. They feed on detritus settling from above, on each other, on whatever resources remain available. Growth ceases, reproduction stops, but individual survival extends through the impact winter for species with low metabolic rates and long lifespans. Sturgeon, deep-sea fish, and other long-lived aquatic species potentially survive as individuals through multi-year impact winters. Amphibians, with their ability to absorb oxygen through skin and tolerate low body temperatures, survive in aquatic and subterranean refugia. Some species burrow into mud and enter estivation, a drought survival strategy that also functions for surviving extended cold periods. Their metabolic rates drop to barely measurable levels. Oxygen demands decrease, and they wait immobile for conditions to improve. Not all individuals survive, but populations persist at reduced levels. invertebrates demonstrate survival through sheer diversity of strategy. Some enter diapause, a programmed developmental arrest that allows surviving unfavourable conditions as eggs, larvae, or adults. Others survive as dormant stages adapted for dispersal cysts, cocoons, desiccated forms that revive when moisture returns. Tardigrades, already famous for extreme stress tolerance, survive impact winter through cryptobiosis, entering a state where metabolism becomes undetectable and the organism tolerates temperature extremes, radiation, and vacuum. The survivors inherit a transformed world. When light eventually returns and temperatures begin rising, they emerge into landscapes barren of vegetation, empty of competitors and predators, offering open ecological niches for those capable of exploiting them. The recovery process favours generalists, opportunists, species capable of rapid reproduction and dispersal, specialists, adapted to narrow ecological niches, find those niches destroyed and face extinction, even if they survive the impact winter itself. Evolutionary trajectories diverge from pre-impact patterns. Isolated populations in different refugia experience different selective pressures and genetic drift in small populations. When populations eventually expand and reconnect, they may have diverged sufficiently to constitute separate species. Impact events thus function as speciation drivers, fragmenting populations and creating opportunities for evolutionary innovation. The fossil record preserves evidence of these processes from past impacts. The end-Cretaceous extinction, caused by the Chicxulub impact, shows sharp decreases in diversity followed by gradual recovery over millions of years. The species that survived mammals, birds, reptiles, fish, invertebrates, plants were not necessarily the most numerous or successful before impact, but rather those with traits enabling survival through the crisis. Their descendants radiated into vacant niches, diversifying and eventually exceeding pre-impact diversity levels. 3I Atlas, if it impacts Earth, would create similar patterns. The survivors would not represent Earth's most conspicuous or abundant species, but rather the cryptic, the small, the metabolically efficient, the adaptable. From these survivors, ecosystems would eventually rebuild, though the timescale extends to thousands or millions of years, and the resulting ecosystems would differ from those that preceded impact. Life persists not through strength or dominance, but through diversity and hidden reserves. Somewhere, something survives, in soil, in stone, in water, in ice, dormant or barely metabolizing, waiting for entropy to cycle back toward conditions permitting growth and reproduction. The planet has cycled through catastrophes before, will cycle through them again. Life continues through the cycles, diminished but unbroken. Only took millions of years to build the diversity that gets filtered down to extremophils and dormant propagules, then millions more to rebuild. The universe trades complexity for time, patiently assembling order only to disassemble it, then beginning again. No progress, just cycles at timescales that make individual lives meaningless. The silence of probability settles over the entire scenario like sediment over ancient bedrock. All of this, the crater, the fires, the impact winter, the ecological collapse exists primarily as mathematics, as models running on computers, as equations describing hypothetical futures that branch from narrow corridors of gravitational interaction. The actual probability of 3I Atlas impacting Earth remains vanishingly small, a number with many zeros after the decimal point, a statistical abstraction that competes with countless other low-probability events for attention and concern. Impact events follow a power law distribution in both size and frequency. Small impacts occur frequently, meteorites delivering grams to kilograms of material strike Earth daily, burning up in the atmosphere or landing as innocuous stones. Larger impacts occur proportionally less frequently. Kilometre-scale objects impact Earth roughly every few 100,000 years. Objects the size of the Chicxulub impactor, 10 kilometres or more in diameter, strike every 100 million years on average. These intervals represent statistical expectations, not regular schedules. The actual timing remains random within these broad averages. 3 Atlas, measuring perhaps a few hundred meters across, falls into a size category that impacts Earth every 10,000 to 100,000 years. But this statistical frequency describes the population of all near-Earth objects, not specifically interstellar visitors. Only 3 confirmed interstellar objects have been detected passing through the solar system in the telescopic era. The population size remains poorly constrained, the detection efficiency uncertain. Extrapolating from 3 detections to a population estimate involves assumptions about size distribution, velocity distribution, and the fraction of interstellar objects that approach close enough for detection. The probability that any specific interstellar object impacts Earth depends on orbital dynamics and the statistical mechanics of gravitational interactions. The solar system consists mostly of empty space. Earth represents a target 8,000 miles wide moving through a region billions of miles across. The cross-section for collision, even accounting for gravitational focusing, remains minuscule compared to the volume of space an object might traverse. Most trajectories lead to near misses, passages within millions of kilometers that qualify as close approaches by astronomical standards, but represent enormous distances by terrestrial measures. Jupiter's role as gravitational wildcard introduces additional uncertainty, but generally functions more as shield than threat. The gas giant, positioned in the outer solar system and possessing enormous gravitational influence, captures or deflects many objects that might otherwise approach the inner planets. Comet Shoemaker-Levy 9's capture and subsequent impact demonstrated Jupiter's ability to intercept threats. Simulations suggest Jupiter prevents more impacts than it causes, though specific cases depend on detailed orbital geometry that cannot be predicted far in advance. The human tendency to focus on worst-case scenarios reflects cognitive biases evolved for survival in environments where threat detection carried greater fitness benefits than ignoring potential dangers. A false positive perceiving threat where none exists costs time and energy. A false negative failing to perceive actual threat costs life. Natural selection favoured erring on the side of caution, perceiving patterns in noise, attributing agency to randomness, and preparing for improbable catastrophes. These cognitive tendencies served hunter-gatherers well, but lead to systematic errors in probability estimation in modern contexts. Media coverage amplifies these biases, selecting for dramatic scenarios over statistical likely outcomes. A story about an interstellar object safely passing through the solar system generates less engagement than speculation about impact catastrophe, even when the safe passage represents far higher probability. The economic incentives of attention-based media favour sensationalism over accuracy, creating distorted public understanding of actual risks. The objective risk from 3I Atlas approaches 0 for practical purposes. Current observations and trajectory calculations show the object on a path that will not intersect Earth. The uncertainty cone has collapsed sufficiently through repeated measurements that impact scenarios can be excluded with high confidence. The object will pass through the inner solar system, perhaps approaching within several million kilometers of Earth, close by astronomical standards but presenting no collision risk. Even if trajectory uncertainties were larger, the base rate of impacts remains so low that any individual object poses minimal threat. Statistically, the risk of impact from unknown, undetected objects exceeds the risk from known, tracked objects by orders of magnitude. The greatest threat comes not from objects being observed and discussed, but from those too small or too dark or approaching from poorly monitored directions, arriving without warning. The worst-case scenario, while physically possible and accurately modelled, remains profoundly unlikely. It serves primarily as thought experiment, as tool for understanding impact physics and extinction mechanisms, not as prediction requiring immediate response. The scientific and civil defense communities conduct such analyses not because any specific object threatens Earth, but because understanding the possibilities enables better preparation for actual threats when they eventually arise. Preparation takes forms ranging from detection programs that identify potentially hazardous objects decades in advance, to deflection mission planning that develops technologies for altering asteroid trajectories, to disaster response planning that considers scenarios beyond typical terrestrial catastrophes. These preparations yield benefits even if impacts remain rare. As the technologies and organizational structures developed for planetary defense often find applications in other domains. The universe generates threats continuously: asteroids, comets, interstellar objects, solar flares, gamma-ray bursts, supernova shock waves, each with characteristic timescales and probabilities. Some threats, like gamma-ray bursts from nearby stars, remain beyond human capacity to prevent or mitigate, their probabilities low enough that concern approaches fatalism. Other threats, like asteroid impacts, fall within the envelope of detection and deflection capabilities, problems that engineering and resources can address if applied sufficiently far in advance. 3i Atlas represents a particular category of threat, rarer than asteroidal impacts but potentially more energetic, arriving from directions less monitored, with trajectories less predictable. The object provokes discussion precisely because it represents something unusual, a visitor from beyond the solar system carrying velocity and composition from elsewhere. But unusual does not mean imminent, and possibility does not equal probability. The object continues its trajectory, following the mathematics of celestial mechanics, bending through Jupiter's gravitational field, arcing through the inner solar system, accelerating around the Sun, and departing back into interstellar space. It carries no intent, holds no malice, knows nothing of the calculation tracking its motion or the scenarios imagined by minds it cannot perceive. It simply falls, as all things fall, through the curved space-time of the solar system's gravitational architecture. The worst-case scenario remains theoretical, a mathematical exploration of consequences that will not occur, at least not this time, not from this object. But the physics remains valid, the models accurate, the mechanisms real. Somewhere, sometime, another object will arrive, will thread the improbable needle of orbital convergence, and the worst case will transition from theoretical to actual. The universe ensures such events eventually, given sufficient time. Only took billions of years for intelligence to arise that can contemplate its own extinction by cosmic accident. Still can't prevent it, just calculate it, imagine it, wait for it. Hope the calculations indicate passage rather than collision. The universe doesn't distinguish between hope and inevitability, renders both equally irrelevant in the long arithmetic of orbital mechanics. The darkness persists, but gradually, imperceptibly, the stratosphere begins to clear. Dust particles settle according to Stokes' law, their terminal velocities determined by size and density, falling through air with infinite patience. The largest particles descend first, completing their journey from stratosphere to surface in months. Smaller particles remain suspended longer, years passing before they touch ground. The finest aerosols, submicron fragments of vaporized rock and soot, drift in the upper atmosphere for a decade or more, gradually dispersing, gradually thinning, allowing incrementally more sunlight to penetrate. The brightening happens too slowly for any observer to notice day-to-day changes. But year to year, light levels increase measurably. Photometers record the transition, instruments documenting what eyes cannot perceive: the gradual return of photons, the slow restoration of energy input that might, eventually, permit photosynthesis to resume. The light returns not as sunrise after night, but as the ending of eclipse, a progressive unveiling of the sun's face from behind a veil that thins but never fully disappears. Temperatures respond to increased solar input, but the response lags, delayed by thermal inertia of ice sheets and deep ocean. The ice, once established, resists melting. Albedo feedback operates in both directions as temperatures rise. Ice begins melting at the margins, exposing darker surfaces that absorb more sunlight, accelerating warming. But the process extends over centuries, the ice sheets persisting long after atmospheric clearing permits adequate solar heating. Somewhere in soil, a seed responds to warmth and moisture. Chemical signals within the seed coat register changing conditions, triggering enzymatic processes that break dormancy. The seed imbibes water, swells, and a radical emerges, pushing downward into substrate. Days later, a shoot emerges upward, seeking light. The seedling carries energy reserves from the parent plant, stored years or decades earlier, now fueling the first tentative reassembly of terrestrial ecosystems. Other seeds germinate nearby, scattered across landscapes slowly being released from ice and ash. The plants grow slowly in thin soils and low light, but they grow. Green returns to earth, patchy and sparse initially, gradually thickening as plants establish, reproduce, and spread. The vegetation traps dust, stabilizes soil, begins the patient work of building organic matter and nutrient cycles from mineral substrate and atmospheric gases. Insects emerge from dormancy, their life cycles resuming after years of suspension. They find the young plants, begin feeding, pollinating, dispersing seeds. Birds return to regions they abandoned, following resources that appear gradually across recovering landscapes. Small mammals expand from refugia, following corridors of vegetation into previously barren areas. The animals carry seeds in their fur and feces, accelerating plant dispersal, connecting isolated populations, slowly knitting together the fragmented survivors into networks that resemble ecosystems. The ocean warms from below, deep waters gradually mixing with surface layers, transferring stored heat upward. Phytoplankton blooms begin appearing in surface waters where light penetration exceeds photosynthetic thresholds. The blooms start small, scattered patches of productivity in an otherwise barren ocean, but they expand and intensify as conditions improve. The oceanic food web begins reassembling, zooplankton grazing the phytoplankton, small fish eating zooplankton, larger fish eating smaller fish. The trophic structure rebuilding layer by layer. The crater remains, a permanent feature slowly filling with sediment and water. Lakes form in the depression, their water chemistry gradually normalizing as rainwater dilutes impact-derived compounds. Pioneer organisms colonize the crater lake's algae, bacteria, simple invertebrates. Over centuries, the crater ecosystem complexifies. Though it will never fully erase the evidence of impact, the rock remembers, carries the shocked minerals and melted spherules as permanent testimony. Somewhere in deep ocean, a whale breaches, exhaling vapor into cold air. The whale descended from survivors that persisted through impact winter in deep water, feeding on what resources remained, waiting through years of darkness for conditions to improve. Its ancestors survived, and now it swims through recovering seas, following instincts refined over millions of years, unaware of the catastrophe its lineage endured. Time continues its patient erosion of all events, grinding catastrophe into geology, reducing extinction to fossil assemblages, transforming the dramatic into the mundane through the simple accumulation of days. The impact that defined an epoch becomes a boundary layer in stone, a thin horizon of altered minerals separating what came before from what comes after. Future geologists, if any arise, will study this layer, analyze its chemistry, reconstruct the event from physical evidence preserved in rock. But the rock remains silent about experience. Records only facts, temperatures, pressures, compositions, sequences. The suffering of organisms during impact winter leaves no trace. The extinctions appear only as absences in the fossil record, species present below the boundary, but absent above. The recovery appears as renewed diversity, new species evolving to fill vacant niches. The record shows pattern without emotion, consequence without meaning. The universe continues generating impacts: supernovae, gamma-ray bursts, black hole collisions, all the violent phenomena that punctuate cosmic history. These events occur without purpose or intention, following physical laws indifferent to outcomes. Matter and energy flow according to thermodynamics and gravitation, creating complexity through random processes and destroying it through entropy, cycling endlessly through states that matter only to the temporary configurations that achieve consciousness and contemplate their own impermanence. Earth orbits the Sun orbits the galactic center. The galaxy moves through space carrying its hundreds of billions of stars and their attendant planets. Somewhere in this vast ensemble, other impacts occur, other extinctions unfold, other ecosystems collapse and recover. The processes repeat across space and time, variations on themes determined by physics and chemistry, playing out wherever matter accumulates and energy flows. The worst-case scenario fades back into probability space, unrealized potential returning to the realm of hypothetical futures. The actual future continues assembling itself moment by moment, constrained by physical law but not determined in detail, allowing space for contingency, for accident, for the unpredictable specificity of real events rather than modelled possibilities. Somewhere, an astronomer closes a computer file containing trajectory calculations for 3i Atlas. The object has passed, continuing outward toward interstellar space, accelerating as it falls away from the Sun's gravity well. In a few years it will cross the heliopause, returning to the interstellar medium from which it came, carrying information about the solar system back into the dark between stars. Perhaps it will encounter another stellar system in a few million years, perhaps not. It continues, indifferent, a fragment of ice and stone following its trajectory through empty space. And Earth continues as well, spinning through sunlight, carrying its cargo of organisms through another day, another orbit, another million years. The planet persists, patient as stone, enduring as gravity, waiting for nothing, expecting nothing, simply existing in the long now of geological time where catastrophe and calm occupy the same continuous moment, separated only by the arbitrary divisions consciousness imposes on duration. Sleep well,